In the next two videos, I'll describe how I adapted CP/M to the 8080 computer I built and demonstrate some of the code I've written to test the disk drives attached to the computer. This code becomes the foundation for creating the CP/M file system and creating some utilities for booting and installing the CP/M OS. Let's start by reviewing the 8080 computer specifications. In this machine, there's an Intel 8080 microprocessor, which is clocked at around 2.2 megahertz. There's 64 kilobytes of static RAM, 1 to 32 kilobyte flash ROM, 128 megabyte ATA compact flash drive, an Intel 8250 serial port with TTL and RS-232 interfaces, and a 60-watt power supply providing +5, -5, and +12. A quick review of the 8080 memory and I/O map. The 8080 provides a 64 kilobyte memory space with addresses from 0000 to FFFF, which is the equivalent to 0 to 65535 bytes. And one of the nice things about the 8080 is that it provides a separate and independent I/O address space from 00 to FF. So you get 256 I/O addresses. This is really useful for keeping devices out of the memory space so that you can have 64 kilobytes of RAM and then up to 256 I/O addresses. This I/O address space works great for serial ports, parallel ports, and a number of different I/O types of devices that are register-oriented. It did not work so well for things like CRT controllers that had video RAM that the CPU needed to access. In that case, those devices tend to be mapped into the memory address space. After reset, ROM 0 starts at address 0, and that's where the monitor initially resides. And then RAM 0, the first RAM chip, is at address 8000. And RAM 1, the second RAM chip, is not in the memory map. After the monitor has come up, one of the first things it does is copy itself into RAM 0. The next thing it does is an I/O write, which changes the memory map. Suddenly, ROM 0 is no longer accessible. It's no longer in the memory map. RAM 0 takes the place of ROM 0, starting at address 0000. And then RAM 1, which was initially out of the memory map, now comes in at 8000. And execution continues from there. In the I/O device map, I've got really only two devices. I've got an 8250 serial port, and then I have my ATA drive. The 8250 serial port's very simple. It's got a set of 8 registers. The data in and out register is at I/O address 0. The line status register is at address 05. And it's really easy to use. It's very easy to write code for, almost trivial to write I/O code for the serial port. The ATA drive is divided up into 2 register sets. There's a CS1 and a CS2 register set. The primary register set is CS1, and you can see the registers that are here, allowing you to control the ATA drive, configure it, do reads and writes, and things like that. The second set of registers is not really used all that much. There's only 2 that you can actually do anything with at address 86 and 87, an alternate status register, which contains some of the same bits as the status register in CS1. And then there's some drive control and drive address logic that we don't really use in this machine. The compact flash card here, it's a 120 megabyte card. This is just a generic card. You can get 2 of them for around $20. Very cheap and easy to use. I find that these 128 megabyte flash cards also support 8-bit transfers, which is really nice. Hard disks, ATA hard disks, generally don't, but most of these flash cards will. I take this flash card and just plug it into a StarTech ATA to CF adapter. It's about $24. Now this is where the first problem occurs. If you look at the flash drive information here, I've got 978 cylinders in 8 heads and 32 sectors per cylinder. This is the standard CHS format. Most ATA drives will automatically come up in this mode. But look at what CPM supports. It supports a maximum of 256 tracks per drive and 256 sectors per track. It's really difficult to get that mapped in. So because you can look at the ATA side, it's got cylinders, heads, and sectors, where CPM is just track and sectors. It can be a challenge to figure out how to get this CF drive mapped to something that CPM can use. Well, it turns out the solution to that's very simple. Just use logical block addressing mode. ATA drives support both. It'll automatically start in CHS mode, but then you can change it to LBA mode. And the neat thing about LBA mode is that now you no longer have CHS. You don't have cylinders, heads, and sectors. You just have sectors. And it starts from 0 to the maximum number of sectors that your drive will support. That's going to be easier to map in some way into CPM's tracks and sectors model. You can see in my drive that my first sector starts with all zeros. So LBA1, LBA2, these are registers in the drive. LBA1, LBA2, LBA3 are all zeros. The upper bits of LBA3 and the lower bits of LBA4 are not used because this drive's only 128 meg. It's never going to be able to use those upper bits. But the lower bits, notice how that's laid out. My last sector is all ones in LBA1 and then a variety of ones in LBA2 and all ones in LBA3. That gives me sector number 3D1FF. 250,368 total sectors in this disk. Now notice that in CPM, the maximum bytes in a disk that are supported is around 8 meg. So I've got 128 meg in the CF drive, but CPM will only support 8 meg in a drive. So I'm going to need to break this drive up. If I want to use all of the space efficiently on this compact flash drive, I'm going to have to create virtual disks. With LBA mode, this actually becomes pretty simple. This is how I did it. What I did is I allocated the lower 6 bits of LBA1 as my sector address. And then I took the upper 2 bits of LBA1 and combined it with the lower 6 bits of LBA2 to make an 8-bit track address. And then I took the upper 4 bits that were left, 2 bits here and 2 bits here, and I made those my disk address. So I've got sector numbers, track numbers, and disk numbers. And you can see for a given disk, the sectors will always start off, sector address will always start off with all zeros. Same thing for the first track will always be all zeros. Rolling up to all ones in the sector address, and then all ones in the track address. So that gives me a starting track, starting sector of 0, and then an ending track of 255, sector 63. So you get 64 sectors in a disk, 256 tracks in a disk. And these bits could potentially give me 16 CPM drives. That still leaves me with one problem, and that problem is that my CF drive supports 512 byte sectors, and that's all, whereas CPM is expecting 128 byte sectors. So I could just map things the way they are. I would be wasting 3/4 of the drive. So the question is, how am I going to maximize utilization of this CF drive with CPM? It turns out the answer is very simple. Just put this CF drive in 8-bit transfer mode and then use the CPM deblocking functions. The deblocking functions will take a physical sector, like sector 0, and create 4 logical sectors. Notice sector 0 has logical sector 0 through 3. Whereas my last sector on the disk, last physical sector, 63, by the time you get to the end of the disk, is logical sector 252 through 255. As it turns out, I can really only get 15 logical drives because logical drive number 16 only has about half of the sectors that it needs. So I'm just going to leave that off. I'm just not going to use those sectors. I'll just have drives 0 through 14. In CPM terms, that'll be drive A through O. But each of those drives will have 8 megabytes each. Now that's an enormous amount of space for a CPM file system. Just a quick review of the CPM disk layout. It's composed of 3 major regions. Track 0 and Track 1 are bootloader and CPM image. Track 2 begins the directory, and after that is user data. That's where your files reside. What CPM does is it breaks up this user and directory area into allocation blocks. Allocation block 0 is the beginning of the directory, and that will roll up to as many directory blocks as are required, as were configured for the file system. And then after that, all the way up to the last allocation block on the disk. Now we need just to review what the physical space looks like and what the logical space will look like. The physical disk geometry, I'll have 15 disks, 256 tracks per disk, 64 physical sectors, 512 bytes per sector, which gives me about 8.38 megabytes per disk. But using the CPM deblocking algorithms, I'll have 15 logical disks, 256 logical tracks, 256 logical sectors of 128 bytes each, still giving me around 8 megabytes per disk. And then I'm going to have one track reserved for the CPM image. I put the bootloader in the monitor, so I don't need it on disk, and my track is so large, it more than holds the entire CPM image. So I'm just going to reserve track 0 for the CPM image. I'll leave sector 0 available on that track if I ever want to put a bootloader there. So how does this work out for CPM? I'll have 255 tracks because remember I'm reserving one track for the CPM image. So I'll have 255 tracks for directory and files. Logical sectors per track is 256. I chose an allocation block size of 4096. Now there's 6 choices here. It could have been 1024, 2048, 4096, 8192, or 16384. The choices here are yours to make. A smaller block size can result in better utilization of disk space, but it can require a lot of directory entries. Whereas a larger block size, not as efficient, but requires fewer directory entries. I choose the middle ground. I just pick 4096. Now, later I might experiment with larger block sizes just to see how the system performs, but for right now, I just pick 4096, middle ground, good choice. Great place to start with a hard drive. Directory entries can be any value that when multiplied by 32 fit evenly in an allocation block. Each directory entry is 32 bytes in size. So here's an example. I chose 1024 directory entries. That was just an arbitrary choice on my part. Each one of those is 32 bytes in size. That means I'm going to need 32,768 bytes for this directory of 1024 entries. You divide that by your allocation block size, that means I'm going to need 8 blocks for the directory. So this is what my disk layout looks like. I've got track 0 reserved for the CPM image, and then I've got block 0 begins the directory. Allocation block 7 is the end of the directory. Then allocation block 8 begins user data, and that rolls on up to block 2039. It turns out CPM is very flexible by allowing lots of choices in how you want to lay out your file system. But that comes with a disadvantage in that if 2 machines, let's say your neighbor has a CPM machine across the street, you may not be able to exchange floppy disks because of all of these different ways that you could lay out your file system. My file system may be totally different from my neighbor's file system. And then you had, in the past, 8-inch disks, 5.25-inch disks, double-sided, single-sided, double density, single density. So many choices. Caused all kinds of problems with interoperability. Just a few additional notes on CP/M disks. Track and sectors are always offset 0. If you know something about CHS controllers, the various different types that were available in the market at this time, most of those started at sector offset 1. And that sector translation table would provide for interleave as well. But we don't need interleave on an IDE drive. It's so fast, we don't need to do anything like that. So we don't use the sector translation table at all. And since LBA mode supports offset 0, we don't have to do anything at all with this sector translation table. Allocation blocks are offset 0. Track 0, sector 0 is reserved for the bootloader. Now my 8080, I placed the bootloader in the monitor. So my sector 0, track 0, sector 0 has nothing in it. My track 0, sector 1 begins the CP/M image. When folks are tinkering with CP/M, this tends to be the place where things get hung up. The CP/M disk parameter block. It's mostly explained in the adaptation documentation for CP/M, but not completely. It's well explained in a few books. You have to really read closely to figure this out. But it turns out it's not really that hard to understand. I'm going to describe it right now. So the first entry, SPT, for my machine is 256. It's just asking for what's the logical sectors per track. Well, I've got, as you saw in previous slides, logical sectors per track is 256. The CP/M adaptation guide gives you this chart for block size. So I chose a 4096 block size. To fill out BSH and BLM, I just had to look at this table. 4096, shift factor is 5, mask is 31, so that's what I put in my disk parameter block. This next one is also simple. Remember in previous slides, I had 2040 allocation blocks. So clearly that's more than 256, so that's going to be a 1. EXM is a 1. And then DSM is just asking for, just give me the total number of logical blocks minus 1. So I had 2040 minus 1 is 2039. Also remember in a previous slide I mentioned that I made the choice, the arbitrary choice of having 1024 directory entries. I could have chosen any other number, but I just decided 1024 sounded good to me. So all that's asking for is give me total number of directories minus 1. So that's 1023. Now this one's the confusing one because it's a bitmap. It's not really a value. So what's happening here is that each one of these bits, 0 through 7, is a block allocated for the directory. Starting with AL0, most significant bit 7, rolling all the way across, AL0 bit 7 is allocation block 0. And then AL0 bit 6 is allocation block 1. So you've got 0 through 7 allocation blocks for the directory, and then 8 through F allocation blocks for the directory. Remember an earlier slide, in order to get 1024 directory entries, I only needed 8 4096 byte blocks. So I'm going to need 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. These 8 bits are what allocate 8 blocks starting at block 0 all the way to block 7. And then these are zeros, meaning we're not going to allocate a directory for these blocks. Check sizes, when you log into a disk, do you want me to do a checksum on the directory? I don't want to do that, so I made that a 0. I don't need to. It's a fixed disk, so usually nothing goes wrong with those. Floppy disk, okay, I can understand it. Fixed disk, nah, probably not. So I made that a 0. OFF, what this number really means is, where does the directory and user space begin? Well, mine begins at track 1, track 0 is for my CP/M image. Now, OFF could also be used to create logical disks, but it was much easier for me to use the LBA simply because the maximum disk size is 8 megabytes, And this offset would only allow me to break up an 8 megabyte disk into logical disks. I didn't want to do that. I wanted to have 8 megabyte logical disks. So now a little bit about CP/M disk driver development. Once you have this information, we can now start working on it. And here's the general steps I followed. First, review the disk controller documentation. And here's the documentation I used. You can find this on the internet. And there's a lot of different versions of this stuff, so you can easily locate one specific to the card you've purchased. Mine have an Hitachi controller inside of them. So this document worked really well. Just about any document probably work as well because ATA specifications have been standardized since 1990. So you should have no trouble using some other manufacturer's document to get an idea how your ATA drive will work. So I use this. The second thing I used is this excellent book, The Programmer's CP/M Handbook by Andy Johnson Laird. This is a really good handbook on all of the internals of CP/M. I use this extensively to figure out that disk allocation block that I described earlier. This is available on the internet as well with a web search. I think it's on archive.org. Definitely download this if you're interested in CP/M and read it. It's a very good resource. Next, define the disk controller in an 8080 assembly file. So start your assembly file. That's what I do. I just try to create a model of the disk controller using 8080 equates. After that, create and test your disk controller initialization for desired operating modes. You want to initialize the disk controller for 8-bit mode and LBA mode. Those are the two most important ones. After that, you can create and test the utility to collect disk parameters. That'll tell you how many total sectors you have in LBA mode and gives you some other information about who made the controller, what the software version is for the controller, and some other useful information. After that, create and test sector read operation, create and test sector write operation. The above initialization read and write code will be used to create the disk driver portion of the CP/M BIOS. Let's take a look at a couple of demonstrations. When you're learning about ATA drives, first place to start is with the register definitions. That's what you see on the screen here. The register definitions page will tell you what all of these different registers do and what the bits mean in them. Because there's quite a few registers in an ATA drive, it does require some reading and some explanation. The next section to review is the ATA command section. This will tell you what commands your ATA drive will respond to and what register settings are required to use that command. The first command I start with is identify drive. It uses command code EC, but you don't have to do anything with the other registers. I'll show you how that works. Here's the code I wrote. It serves as the basis for all of the other functions I'm going to test. If you remember in a previous slide, I mentioned that create a model of the ATA drive. What I've done with these equates is I've recorded every register for these ATA drives. And then I've recorded the commands that are of interest, the commands that my ATA drive will respond to. I've also recorded the error and status flags and the various feature codes that would be used for the features command. After that, I've got an ATA sector buffer that begins at address 2000. I'm going to use a few of the monitor routines. Monitor start, so I want to be able to go back to the monitor when this program exits. I'm using the console out routine for output messages and the print routine to print messages to the console. This program starts at address 1000. So the first thing I do is set the drive into 8-bit mode. That's simple to do. I start off loading the feature 8-bit on into register A, and then I'm going to output that to the features register. I'm going to load the command set features in A and store that in the ATA command register, which is going to start that feature setting. It's going to turn the 8-bit mode on. The rest of this code is just to collect identify information from the disk buffer. After that, I'm going to call print info. That's going to print the information the identify command returned. Let's give it a try. First, I'm going to copy in my program in hex format. I'm going to paste it into the monitor. And then I'm going to run it. And that's now printed out the information from the drive itself. I've got 3D2 cylinders, 8 heads, 20 sectors per track. You'll remember that on previous slides that I'm in CHS mode by default on power up, and that gives me 3D 200 sectors. It also shows the serial number for the CF drive and who made the controller. It's the Hitachi controller and what firmware version is available. This total sectors 3D 200 is needed for LBA mode. This tells you what the total number of sectors will be. Now I want to try reading a sector from a disk. I'm using the same equates that I used in the Identify program. I'm setting it up in 8-bit mode, but I'm also setting it up, you'll see down here, in LBA mode. So I'm no longer using CHS. I'm going to set it up for LBA, and I'll be using these registers, LBA bits 0 through 7, LBA bits 8 through 15, LBA bits 16 through 23, and 24 through 7. And I'm just going to read the very first sector. So all of these bits are going to be set to 0. That's what happens until we get down to where all of the action is, and that's where I'm giving it the command read sector with retry. So I'm going to set all of these LBA bits to 0, and then I'm going to load my command read sector retry into register A, and then put register A into the ATA command register of the drive, and that's going to execute that command. And then, of course, the rest of the code is just collecting the data out of the disk buffer and putting it in the sector buffer at address 2000. First, let's take a look at what's in the sector buffer at address 2000. Bunch of random stuff. I'm going to fill the sector buffer with zeros. So fill with 0, 0. Now let's dump it again. It's all zeros. Now I'm going to run the sector read command. So to do that, I want to copy in hex file. I want to load it, paste it, and then run it. Since it's completed, let's take a look at the sector buffer. It's all E5s, and that's what it should be. I've run some previous reads, writes, testing some formatting utilities, and I left all of those at E5. But let's see if we can write them. Let's see if we can change them to something like FF. Let's take a look at the write code. Same thing, all of the equates, identical to what we've used before. And the only thing that I've done is I'm putting in 8-bit mode like I did before, putting in an LBA mode like I did before. I'm using command write with sector retry this time. And I've changed these routines down here to move data from the sector buffer into the disk buffer versus the other way around. Let's give it a try. I'm going to copy in the code in hex format. What I want to do now is I want to change the sector buffer to what I want on the disks. So let's fill that. I'm going to fill address 2000, 2200, fill it with FF. Now let's dump that. It's all Fs. Let's load our program, paste it in, run it, and it says it's completed. Let's see what's in the disk buffer. Let's clear that. Make it all zeros. Dump just to check. It's all zeros. Now let's read the disk and see if our FFs are there. Going to copy in the read program, load it, paste it, run it. So we've successfully read that sector. Let's take a look at the disk buffer. All Fs. Excellent. So this shows me that my read and write utilities are functioning as I expect. Now I'm ready to move on to more complex CP/M adaptation. I'm going to cover that in the next video, and I'll expand it with my disk driver and my I/O utilities, adding in the CP/M deblocking routines, and then we'll test that. After that, I'm going to create a format utility, a loader utility, a CP/M store utility for writing CP/M images to disks, and then we're going to boot CP/M and see how it works. So stay tuned for the next video when a lot of the action is going to happen.